Call of Duty Mobile won the Mobile Game of the Year award, and it achieved a monthly revenue peak of $40 million in December of 2023. Why is he even talking about this game? Hold your horses, because in today's video, we are going in big. I play this game a lot, and I'm quite sure you have either seen a clip of this game being played online, or you have played it yourself, or you have seen an advert of this game, or your friend has told you about it. And if not this particular game, then there are other games that somebody must have told you about, or you love playing yourself. Then again, has your curiosity ever driven you to wonder how the hell these video games work? Like, how do they even simulate real world environment? Things like a bullet traveling through space and time. How do characters run around at different speeds? And how do they jump from a rooftop to a floor? How do they even climb buildings? How do they even simulate gravity? There are so many questions we could ask ourselves about how video games work, but we will sum it up in one sentence. How do these games simulate real world physics? Well, what better way to learn about physics simulation than to code up your own basic physics simulation engine using everybody's favorite programming language? Wait for it, JavaScript. In today's video, we will code up our very own physics engine using JavaScript, starting from a very basic vector class and word simulation to a classical physics simulation, implementing different types of forces on objects and bodies in the simulation. It will condense with us building a 2D game using HTML, CSS, and JavaScript based on the physics engine we are going to implement. We will cover these talking points using two separate videos. The first one will cover the vector, object, and word simulation together with the forces that will act on the bodies in the simulation, and then in a separate video we will build the game. If you think that makes sense, then absolutely smash that like button. Ensure you subscribe to the channel and turn on the bell notification to get access to all of our videos as they drop. Before we begin, I know you want us to jump straight into the code as fast as possible, but today we will have to put on the brakes and get over our fear of maths and physics. You will need to understand some basic physics concepts like vectors, as the full understanding of how the simulation environment will work will depend on these concepts. We need to get these basics out of the way, and there is good news because this will not take any of our time, so we can jump to the fun part as soon as possible. Double good news, because if you already understand how vectors work, you can just jump straight to the section where I start coding up the project straight away. Depending on your familiarity with maths and physics, this might be a simple concept, but if like me you hated maths and physics so much, then be prepared to face your fears. Let's start with vectors. A vector in mathematics and physics is a quantity that has both magnitude and direction. The magnitude refers to the size or length of the vector. The direction indicates the orientation or line of action of the vector. Examples of vectors are velocity, which describes the rate of change of position. We also have displacement, which describes the change in position of an object. We have force, a push or pull on the body that has both magnitude and direction. And acceleration is also a vector, and it is the rate of change of velocity with time. Vectors can be represented in 2D and 3D plane, but for time's sake, our vector implementation will only be concerned with the 2D world. Vector operations involve mathematical calculations performed on vectors, including addition, subtraction, and multiplication. We have both scalar multiplication and dot multiplication. These operations extend the principles of elementary algebra to vectors. First, we need to understand what we mean when we say component of a vector. A component of a vector is the projection of the vector onto one of the coordinate axes, like say the x-axis or the y-axis. For a 2D vector, v its magnitude and an angle theta relative to the position of the x-axis, the components of the vector are the x component, which is v of x, and it is the length of the vector's projection onto the x-axis. It tells you how far the vector extends horizontally. Also have the y component, which is v of y, and it is the length of the vector's projection onto the y-axis. It tells you how far this vector extends vertically. The components of the vector are the building blocks that describes the vector's overall effect in each direction. To add two 2D vectors, you simply add their x components together and the y components together. The result is a new vector C with new x and y components. We can also carry out subtraction on vectors. We treat subtraction of vectors the same way we treat addition of vectors, and at this point you subtract the corresponding components of the two vectors to get a new vector. Scalar multiplication of vectors increases the magnitude of a vector without changing its direction. We can increase that magnitude by a given integer. You can also calculate the magnitude or length of a vector, and it is used to calculate the speed from a velocity vector or the strength of a force vector. Normalization is the process of converting a vector into a unit vector. What the heck is a unit vector? A unit vector is a vector that has a magnitude of exactly 1. The purpose of normalization is to preserve the vector's direction without stripping away its original magnitude. This is incredibly useful because it gives us a pure representation of the direction of a vector, which can then be scaled to any magnitude or length of our choice. Unit vectors are essential for representing direction without magnitude, which is often needed for collision detection. Normalization is the cornerstone of physics engine development, especially for collision detection. It is also used for collision normals. When two objects collide together, the force of collision acts along a specific direction perpendicular to the surface of impact. This direction is referred to as the surface normal, and it is always a unit vector. Normalization can also be used for applying forces. If you have a force of a specific magnitude, let's say 50 newtons, that needs to be applied in a particular direction, you can first get a normalized direction vector and then multiply it by the magnitude, which is 50 newtons. Now let's look at the dot product. The dot product of a vector is an operation that takes two vectors and returns a single number. Unlike vector addition or subtraction, which results in a new vector, the dot product tells you something about the relationship between the two vectors. The dot product is incredibly useful for finding the angle between two vectors, projecting one vector onto another vector by rearranging the geometric formula. You can find the angle between two vectors, which is useful for things like calculating friction or determining how bouncy a collision should be. It is also useful for determining if two vectors are perpendicular, that is, their dot product is exactly 0. We are going to proceed to coding. I will create a new file index.html, and inside this file I will paste in some HTML boilerplate code to serve as a UI for the physics simulation we are building. We have some styles that sets the margin to 0 on the body elements, and overflow is also hidden. Then I will also have some styles for the canvas element where we will set the display to block. We have a canvas element with an ID attribute that is equal to canvas, and finally we are linking to an external script index.js using the script tag. I'm going to create that index.js file, and inside this file I will create a new class vector. I will define a constructor function that accepts two optional arguments, x, which is equal to 0, and y, which is also equal to 0. Remember, these are the components of the vector. In this constructor function, I will set this dot x to be equal to x and this dot y will be equal to the y argument. We need to add methods on this class that will allow us to carry out vector operations, starting with vector additions. I will add a new method, add, which accepts an argument v, which is a vector. And my apologies for not using TypeScript to implement type safety. Inside this method, we will add the x component of the vector to the s component of the argument vector that we passed in, and we'll also do the same thing for the y component and return this from this function to allow for method chaining. I will add a sub method that will be responsible for vector subtraction. This method will accept an argument v, which is a vector, and inside this method I will subtract the x component of the vector from the s component of the argument. I will also do the same for the y component and return this from the function. I will add another method, scale, to handle scalar multiplication of vectors. This method will accept an argument x, which is an integer that we will use to multiply the components of the vector. Inside the function, I will multiply the s component of the vector with the x integer, and I will also multiply the y component of the vector with the same x integer. I will add a length method to the vector class, which calculates the magnitude of the vector, just like we described earlier. And inside this function, we'll multiply the s component of the vector by itself, then add it to the result of multiplying the y component by itself, and then we'll now return the square root of that value, okay? Then I will add a normalized method, and inside this function, I will create a variable length, which is equal to the result of calling this dot length. Then I will check if the length variable is greater than 0. And if that is the case, I will scale the vector using the length variable and return this from the function. Then I will add a copy method that allows us to create a new vector from the components of the current vector. Now we are done with implementing our vector class. I'm going to implement another class body, and this will serve as an object or a body in the simulation. I will define a constructor function inside this class. This constructor function will accept a position argument followed by a velocity argument, which is a vector, which I will set to be an empty vector if no argument is passed in. We will accept an optional mass argument, which will be set to 1. We will accept an optional restitution argument, which will be set to 0.7. The restitution argument controls how objects behave when they bounce, and inside the constructor function I will set this dot position to be equal to the position argument, this dot velocity will be equal to the velocity argument, and this dot mass will be equal to the mass argument, while this dot force will be equal to a new vector. This dot restitution will be equal to the restitution argument. I will define another method, apply force, which applies an external force. This method will accept an argument, and inside this method I will call this dot force dot add. I will add another method, update, which accepts an argument dt, and inside this I will calculate the acceleration of the body using the following formula. F is equals to mass times the acceleration. If force is equals to mass times acceleration, then acceleration will be equals to force all over mass. Then I will call this dot velocity dot add and scale the acceleration by dt. This updates the acceleration of the body, and then I will call position dot add with this dot velocity dot copy dot scale dt to update the position of the body as it moves with acceleration. Then I will set this dot force to be a new empty vector, that is its x and y components are exactly 0. Now we are done with the vector class and the body class. Let's handle the physics word. For that, I will create a new class, physics word. I will add a constructor function which accepts an optional argument, gravity, which is equal to a new vector. The x component will be 0 and the y component will be 9.8, which is the value for acceleration due to gravity. This is to allow us to simulate gravity in the environment, which pulls an object towards the ground. Inside the constructor function, I will set this dot bodies to be equal to an empty array. This dot gravity will be equal to the gravity argument, and this dot ground height will be equal to the canvas dot height. I will define an add body method which accepts a body argument, and inside this function I will push the body into this dot bodies array. I will define an update method which accepts an argument dt. Inside this function I will add a for loop that iterates over the bodies in these dot bodies, and for each body we will apply the gravity force on it and call the update method on the body while passing in dt as an argument to it. I will check if the y component of the body is greater than or equal to the value remaining after we subtract 28 from the ground height, and if that is true, I will set the value of the body dot position dot y to be equal to the result of subtracting 20 from the ground height. Then I will continuously subtract the restitution of the body from the y component of the body's velocity. This is going to allow our objects to fall under the influence of gravity. Okay, now let's create a canvas by creating a new variable canvas, which is equal to the result of calling the document.getElement by id with the canvas as the argument. Then I will create the variable ctx, which will be the result of calling canvas.getContext with 2D. Then I will set the width of the canvas to be equal to the width of the window, and the height of the canvas will be equal to the height of the window. I will create a variable word which is equal to a new physics word, and then I will create a new body which is a ball, and I will add it to the physics word. After creating it, I will add a new function, game loop, and inside this function I will call ctx.clearRect with 0 as the first argument and then 0 as the second argument, and the width of the canvas becomes the third argument, while the height of the canvas is the last argument. I will call word.update, ensuring that we get a 60 fps animation. I will call cts.begin part, and then I will call cts.arc with the x component of the position of the ball and the y component of the position of the ball, 20 as the width, 0, and math.pi times 2 as the last argument to this cts.arc function. Will create a circle for us. Okay, then I will set the ctx.fill style to be red. Then I will call ctx.fill. I will call the request animation frame with the game loop function as an argument, and outside the game loop function I will also call the request animation frame function with game loop function as argument to it. If I go ahead and open up our browser, you can see that we now have a red ball that falls from the top under the influence of gravity, and slowly the ball comes to a halt but it bounces around up and down before it does that, right? Isn't that amazing? If you're enjoying the video, please ensure you leave it a like and make sure you subscribe to the channel so you can get access to all of our video as they drop. Now we have a working engine, but we need to improve on that. First of all, gravity is pulling everything down, so there is no starting from the top. All objects we need to start from the bottom of the world. I will head back to the index.html page where I will add a new div with a class controls, and inside it you will find an embedded text. Click and drag a ball or square to launch it. After it, I will add another text. Hold the drag for more power. Squares and circles repel each other. You get the idea? We want to add different types of shapes, and then I will add an extra force like frictional force, air resistance, magnetic force, and I'll also implement collision detection. We will be making our small world much more realistic, so let's dive in head first. I will add a new method, length square, on the vector class. Forgive my spelling of this method, I'm going to fix it later. Inside this function, we will just square the components of the vector and return it. Then I will add a static method sub which accepts two arguments, v1 and v2, which are vectors. This method is responsible for carrying out component subtraction on the two vectors, creating a new vector with the components. Then I will add a static dot method which accepts two arguments, v1 and v2, both of which are vectors. This performs a dot multiplication on the vectors. Let's edit up the body class starting with the constructor function. I will accept two optional arguments starting with the color, which by default will just be red, and then a shape, which by default will be a circle. Inside the constructor function, I will set this dot shape to be equal to the shape argument, and this dot radius will be equal to 10 minus this dot mass. This dot color will be equal to the color argument. I will add a draw method on the body class which accepts an argument ctx. Inside the function, I will set the ctx dot fill style to be equal to this dot color. Then I will check if this dot shape is equal to circle, and if that is the case, I will call cts dot begin part. Then I will call cts dot arc with the x component of this dot position as the first argument. The y component of this dot position becomes the second argument, and this dot radius becomes the third argument. Y0 becomes the fourth argument, and mat.py becomes the last argument. I will call ctx.fill and check if the shape is square. Then I will create a variable size which is equal to the result of multiplying this dot radius by 2. Then I will call ctx.fillRect. For the first argument, I will subtract the s component of the vector from the radius. I will also subtract the y component of the vector from the radius as the second argument. I will pass in the size as the third and fourth argument. Now, let's modify the physics word class, starting with the constructor function. I will accept a canvas argument, and inside the constructor function, I will set this dot canvas to be equal to the canvas argument. I will set this dot drag coefficient to be equal to 0.005, and this dot friction coefficient will be equal to 0.5. The drag coefficient is the air resistance, while the friction coefficient is the ground friction. I will also modify the update method on the physics word. It will accept three more arguments: mouse position, is dragging, and dragged body. Then I will come down to where we loop through these dot bodies, and for each body I will create a drag force which is equal to body.velocity.copy.k. I will pass minus this dot drag coefficient times the body dot velocity dot length. Remember, calling the length method gives us the magnitude of the vector, and then I'm going to apply the drag force on the body. I will check if the y component of the position of the body is greater than or equal to this dot canvas dot height minus the radius of the body, and if that is true, I will create a variable friction force which can be calculated by calling body.velocity.copy.k with this dot friction coefficient multiplied by the mass of the body, and then I will apply the friction force on the body. Next, we will check if its dragging is false and the drag body is not equal to the current body, and if that is true, I will create a new variable magnetic force which is equal to calling the static sub method on the vector class. I will create another variable distance, which is equal to the magnitude of the magnetic vector. Then I will create another variable magnetic force, which is equal to obtaining the magnitude of the magnetic vector and scaling it up to 500,000 all over the distance minus 1. Forgive my use of magnetic force before we created it. It's supposed to be a magnetic vector. That's a bug I will sort out later. Then I will apply the magnetic force on the body. I will break out of the if statement, and under it we will call this dot check collisions, after which we will call this dot check wall collisions, this dot check repulsive force. All of these functions we will implement shortly. The check collision method handles collision detection. The check wall collisions handle wall collision detection, and the check repulsive force method allows shifts to repair each other. Let's start with the check wall collision method. And inside this method, I will add a for loop that iterates through these dot bodies. And for each body, I will check if the y component of the position of the body is less than or equal to the radius of the body. Then I will set the y component of the position of the body to be equal to the body dot radius. The y component of the velocity of the body will be times equal to minus the restitution of the body, which enables object to bounce off the top of the simulation. Okay. Next, we will need to ensure that object bounce off the ground as well. And for that, I will check if the y component of the position of the body is greater than or equal to this dot canvas dot height minus the radius of the body. And if that is true, I will set the y component of the position of the body to be equal to this dot canvas dot height minus the radius of the body. The y component of the velocity of the body will be times equal to minus the body restitution. We need to handle left and right collisions, and for that, I will check if the x component of the position of the body is less than or equal to the radius of the body, and set the x component of the position of the body to be equal to the radius of the body, and the velocity of the x component of the body will be times equal to minus the restitution of the body. Next, I will check if the x component of the position of the body is greater than or equal to the width of the canvas minus the radius of the body. The x component of the position of the body will be equal to this dot canvas dot width minus the radius of the body, and the x component of the velocity of the body will be times equal to minus the restitution of the body. We are done with that. So let's implement the check collision methods inside this class. And inside this method, I will add a for loop that will run until we get to the end of these dot bodies. And inside it, I will nest another loop that will still run through these dot bodies, but instead of starting at 0, it's going to start at 1. I will create a variable body1, which is equal to this dot bodies dot I, and I've also create a second variable body2, which is equals to this dot bodies dot j. This is to retrieve the colliding bodies. Then I will check for the collision axis by using the static sub method on the vector body2 dot position as the first argument and body1 dot position as the second argument. Then we will calculate the distance square by calling the length square method on the collision axis. Then I will obtain the radii sum by adding the radius of body1 to the radius of body2. I will check if the distance square is less than or equal to the square of the radius sum, and if so, we will obtain the distance by squaring the distance square. The overlap can also be gotten from subtracting the radii sum from the distance. Then I will create a copy of the collision axis and normalize it, store it in a variable normal. Then I will create a variable correction, which is equal to creating a copy of the normal and scaling it up by multiplying the overlap by 0.5. Then I will call body1.position.sub with the correction and body2.position.add with the correction. Okay, that is to enable the two objects to move away from each other after they have collided. I will calculate the relative velocity by using the static sub method, the vector, passing in the velocity of body2 as the first vector and the velocity of body1 as the second vector. I will calculate the relative along normal by calling the static dot method on the vector class, passing in the relative velocity as the first vector and the normal as the second vector. I will check if the velocity along normal is less than 0, and then I will create a variable e, which is equal to the result of calling math.mean, passing in body1 dot restitution as the first argument and body2 dot restitution as the second argument. Okay, this is going to handle the smoothness of the collisions as they are moving away from each other. I will calculate the j scalar and use that to create a variable impulse by copying the normal and scaling it up using the J scalar. Then I will call body1.velocity.sub with a copy of the impulse, scaled up to 1 over the body1.mass. I will call body2.velocity.add with a copy of the impulse, which is scaled up to 1 all over body2.mass. Now we are done with collision detection. We need to implement the check repulsive force method, and inside this method we will add an outer and inner loop that runs using this bodies.length, and for each iteration of the inner loop I will obtain the first body using this bodies.I, and I'll also obtain the second body using this bodies.j. I will check if the shape of body 1 is a circle and if the shape of body 2 is a square. Then I will create a repulsive vector which is gotten by using the static sub method on the vector class, with body 2 the position as the first argument and body 1 the position as the second argument. I will calculate the distance by obtaining the magnitude of the repulsive vector. I will calculate the minimum distance using the radius of body 1 and radius of body 2. I will check if the distance is greater than minimum distance, and then I will calculate the force magnitude by multiplying 100,000 by 1 minus distance all over minimum distance. I'll calculate the repulsive force by obtaining the magnitude of repulsive vector up with minus the force magnitude. Then I will apply a copy of the repulsive vector scaled up to 1 all over body 1 dot mass to the first body. I will also apply a copy of the repulsive vector scaled to 1 all over body 2 dot mass to the second body. Now I will create a function resize canvas, and inside this function I will set the canvas dot width to be equal to the window dot inner width, and set the canvas dot height to be equal to the window dot inner height. Then I will call the resize canvas function. Then I will get rid of the existing body object, and I will add a word dot add body and instantiate a body object. The first will be a vector where the x component will be 100 and the y component will be the canvas dot height minus 20. The second argument, which is the velocity, will be a vector with 0 for both the y and x components. The mass will be 10, the restriction will be 0.8, and the color of the shape will be red. The shape itself will be circle. I will copy and paste this down 3 more times, ensuring I change the position of the second object. The x component of the position vector will be the canvas width minus 100. The mass will be 15. The restitution will be 0.9. The color will be blue. We will leave the shape untouched. For the third body, the restitution will be 0.7. The color will be green. The mass will be 5. The s component of the position will be 250. And for the fourth body, the s component of the position of the vector will be the canvas dot width minus 250. The restitution will be 0.85. The color will be purple and the shape will be square. I will ensure I also change the shape of the third body to be a square. I will create a variable is dragging, which is force. I will create another variable drag body, which is null. I will create another variable start drag position, which will be a new vector. I will create a start drag time variable, which will be equal to 0. I will create another variable mass position, which will be a new vector. Then I will attach an event listener to the mouse that event on the canvas. Inside the event handler function, I will create a new variable rect, which is equal to the result of calling the canvas dot get bounding client rect method. Then I will create another variable mass x, which is the x coordinate of the mass, and it will be equal to the event dot client x minus rect dot left. I will create another variable mass y, which is equal to the y coordinate of the mass. Then I will loop through the word dot bodies, and for each body I will create a new variable distance square. I will check if the shape of the body is a circle, and then I will set the distance to be equal to calling the static sub method of the vector with the position of the body as the vector, and the second argument, which is a new vector with the mouse x as the s component and the mouse y as the y component of that vector. Then I will call the length square method. Otherwise, I will check if the shape of the body is a square. Then I will create a variable dx, which will be equal to math the absolute with the x component of the position of the body minus the mouse x. I will create another variable the y, which is equal to the result of calling the math.abs with the y component of the position of the body minus the mouse y, and the distance will be equal to a conditional. I will check if the y is greater than the radius of the body. If the expression evaluates to true, I will return infinity as the value of the distance square, or 0. Next, I will check if the distance square is less than or equal to the square of the radius of the body and set its dragging to true. The drag body will become the current body we are iterating over, and the start drag position dot x will be equal to the mass x, and the start drag position dot y will be equal to the mass y. The start drag time will be equal to date dot now, and the drag velocity will be equal to a new vector. I will attach an event listener to the mouse move event on the canvas, and inside the event listener function we will create a new variable rect, which will be equal to calling the canvas dot get bounding client rect. I will set the mouse position dot x to be equal to the event dot client x minus the rect dot left. Mouse position dot y will be equal to the event dot client y minus the rect dot stop. Then I will check if its dragging is false and if drag body is null, and return prematurely from the function. I will set the s component of the position of the drag body to be the mouse position dot x, and the y component of the position of the drag body will be equal to the mouse position dot y. I will add another event listener function to the mouse up event on the canvas. I will check if its dragging is false and if drag body is null. Then I'm going to return prematurely from this function. I will create a variable drag vector which is equal to the result of calling the static sub method on the vector class with the mouse position and the start drag position. The drag duration will be equal to the result of calling date.now minus the start drag time all over 1000. I will calculate the first multiplier by adding 1 to the drag duration and multiplying it by 500. I will calculate the launch force by copying the drag vector and scaling it minus the first multiplier. Then I will apply the launch force on the drag body, and I will set its dragging to be false and the drag body will become null. Inside the game loop function, I will create a variable dt which will be equal to the animation frame and pass it into the word.update method. Then I will also pass in the mouse position is dragging drag body to the word.update method. Then I will loop through word.bodies, and for each body I will call the body.draw method with the ctx as an argument to it. Then I will get rid of all the code we don't need anymore. I will comment out 3 bodies, head back to our browser, and you can observe that we have one ball that sticks to the floor by default instead of falling from the top. You can observe that I can drag on the body to launch it, and observe how it moves around and loses momentum with time as it travels through the air. If I add a second ball, now we can observe that the two bodies collide and move away from each other. If I add a third and fourth shape which are squares, you can observe that the body moves quite slowly along the floor due to the simulation of friction, while square and circular bodies will repair each other instead of colliding. We are going to stop here for now. In our next video, we will build on top of this engine, and we are going to implement a very popular 2D game you might have played before now. Want to find out what game that is? Make sure you subscribe to the channel and turn on the bell notification. Leave this video a like so others can find it, and I'm going to see you in that next video.